Welcome back to our series of lessons on linear programming. So far, we've worked with a few linear programming problems and found the feasible regions for these problems by testing a large number of points one by one. We crossed off points that weren't feasible and ended up with a feasible region made up of all the points that weren't crossed off. We also saw that the points crossed off and the points accepted were in groups and that we could separate the groups with straight lines. Then we found that the lines created a boundary around the feasible region. The yellow crosses here showed that the combination of fat units in the two products, Max Health and NutriFood, was less than what we wanted. We didn't cross out points on the other side because the combination of fat units in these points was more than or equal to what we needed. Less than, more than, and equal to are mathematical terms we've used before. They all have to do with equations and inequalities. In this lesson, we look at how linear inequalities and their graphs can help us to define the feasible region in a linear programming problem. So by the end of this lesson, you should be able to draw the graphs of linear inequalities. Let's have another look at the grid with the crossed off points from the previous lesson. We saw that the points were grouped and we put in lines to show the boundaries of the feasible region between those points. Now, if we could work out the equations for these lines, then we won't need to test every single point on the grid to see if it is feasible or not. But what we want to find is not just the equation of the line, but the inequality that represents the line and the crossed off area together. Let me start by reminding you about linear inequalities. But before we go into that, let's welcome back MacGyver, who once again is with us in the studio.
Hi.
What does this expression mean to you?
Oh, that's pretty obvious. It means that x is equals to 5.
Right. And the expression x equals 5 could be the solution of an equation. For example, if we are asked to solve this problem, 3x minus 2 equals 13, we get x equal to 5. So we can say that 5 is the unique value of x that solves the equation or that satisfies the equation. We can say that 3 times 5 is 15 and 15 minus 2 equals 13. The solution is unique because there is no other value of x that will make the statement true, no other value of x that will satisfy the equation. For example, think about x equal to 6. 3 times 6 is 18, and 18 minus 2 equals 16. 16 is certainly not equal to 13. In other words, an x value of 6 does not satisfy the equation. Now look at this algebraic expression here. We read it as 3 times x minus 2 is greater than or equal to 13. This is an inequality, and any value of x that makes 3x minus 2 either equal to 13 or greater than 13 will satisfy the inequality.
So, an x value of 6 satisfies the inequality. When we substitute 6 for x, into the left-hand side of the expression, the inequality, we get 16. And 16 is greater than 13, which is the right-hand side of the inequality.
Exactly. That is a good example of an inequality that uses greater than or equal to. But there are also other inequalities. One amount can be greater than another. One can be less than or equal to another. And one amount can be less than another. Our challenge is to return to the linear programming context and use the inequalities there. In a previous lesson, we worked out the possible ways that MacGyver could use his available time. He wanted to divide his time between soccer and homework. Let's look at that problem again.
In the problem, we had these constraints. I planned to get up somewhere between 7:30 and 9 o'clock in the morning, and I needed to leave to watch the soccer game at 11:30. I spent an hour washing and having breakfast. That left me with more than 1.5, but less than 3 hours to choose between playing soccer and doing homework.
So the time spent doing homework plus the time spent playing soccer has to be less than or equal to 3 hours. To make this easier to work with, we can use variables. Let's use X for homework and Y for soccer. So we can say, let X be the number of hours spent doing homework and Y be the number of hours spent playing soccer. Then this constraint becomes X plus Y must be less than or equal to 3. This tells us that X together with Y must be less than or equal to 3, and this statement is called an inequality. Now we have set up an inequality and we can solve it. We need to find all the combinations of X and Y that together add up to 3 hours or less. If X is 1 and Y is 1, X plus Y equals 2, and 2 is less than 3. So that works. We say the pair of values 1, 1 satisfies the inequality. That's one solution to the inequality. Can you suggest another one?
How about X equal to 2 and Y equals to 1? Then X plus Y is 2 plus 1, which equals 3. We can have an answer equal to 3. So the pair of values 2, 1 also satisfies the inequality.
Right. And X equal to 1 and Y equal to 2 will also work. How about the pair 2, 2? 4 is greater than 3, so that pair doesn't work. Now we also need to remember that we can use half hours as well. So let's try an X value of 1/2 and a Y value of 1.5. That comes to 2, so that pair also works. Have a look at these pairs of values. Some pairs add up to 3 exactly, so they satisfy the inequality. Some add up to less than 3, so they also satisfy the inequality. Then there are pairs like this that add up to more than 3, but they don't satisfy the inequality.
In other words, points that satisfy the equal part of the less than or equal to, and points that satisfy the less than of the less than or equals to, or points that do not satisfy the less than or equal to at all.
Now we need to see if we can use the inequality to draw a graph. The graph should show us the same information as the grid we developed when we tested each point in a previous lesson. First, let's identify the points that satisfy the equal part of the inequality. These are points that satisfy the equation x plus y equals 3.
Isn't that just an equation for a straight line graph?
You're right. If I subtract x from both sides of the equation, I get y equals minus x plus 3.
That's quite easy to draw. The y-intercept is at x equal to 0 in the equation, so y is 3. That's the point 0, 3 over here. I can find the x-intercept by making y equal to 0 in the equation. That gives me x equals to 3, which is the point 3, 0. And I can just join the points with the straight line.
Well done. Now let's look at the points we tested earlier, 1, 2 and 2, 1. They gave us exactly 3. 1, 2 and 2, 1 both lie on the line you've drawn. So this line represents all of the points that satisfy the equal to part of less than or equal to. Now, how can we show the points that are represented by the less than part of less than or equal to?
We worked out one of those points already. It was 1, 1.
We've already seen that the points are grouped and that there are lines that divide the points into those we had to cross off and those that were in the feasible region.
Does that mean that any point on the same side of the line as the point 1, 1 will satisfy the less than part of the less than or equal to?
That's a good conjecture. Let's test a few points to see if you're right.
How about this point? It has an x value of 0 and a y value of 2. 0 and 2 together give 2. That's less than 3. So it does fit the less than part of the inequality.
Well done. Try another point.
Okay, this point 1, 0. Yes, it works. It also fits the less than part.
Great. So these 3 points are all on the same side of the line and they all fit the less than part of the inequality. If you carry on plotting points that fit the inequality, you will find that they all lie in this area below the line. So the line represents the equation x plus y equals 3, which divides the graph into 2 regions. A region with points that satisfy the inequality x plus y less than 3, and a region of points that don't. We can show that all the points in this region satisfy the inequality by coloring in the region.
So, the points on the straight line and in this region together represent the points that satisfy the inequality x plus y is less than or equals to 3. That means this region represents all possible points that add up to exactly 3 hours or less than 3 hours of time, and shows all the possible combinations of time spent playing soccer and time spent doing homework in the 3 hours available for these activities. Wow, that's a lot easier than testing every point.
Now let's see if we can do the same kind of graphing for the problem about the best mix for a nutritional supplement. Let's look at the dietitian's problem. She wants to mix 2 products, Max Health and NutriFood, in a way that gives the best possible mix of nutrients but costs the least. Let's look at the units of carbohydrates needed in the mix. Each scoop of Max Health contains 2 units of carbohydrates and each scoop of NutriFood contains 4 units of carbohydrates. The mixture for the patient must contain 20 or more units of carbohydrates in each serving. It helps to write it down in words first. We could say the units of carbohydrates from Max Health plus the units of carbohydrates from NutriFood must add up to 20 or more. Now let's use variables to make an inequality. Let's say x is the number of scoops of Max Health and y is the number of scoops of NutriFood. Can you write a linear inequality using x and y?
Each scoop of Max Health has 2 units of carbohydrates, and x is the number of scoops. So that's 2 times x.
That makes sense, doesn't it? Each scoop contains 2 units, and x is the number of scoops. So 2 times x will give us the total number of carbohydrates from Max Health.
Okay, so each scoop of Nutri-Food has 4 units of carbohydrates, and y is the number of scoops. So we write down 4 times y.
Quite right. So the algebraic version becomes 2 times x plus 4 times y is greater than or equal to 20. This tells us that the combination of scoops of Max Health and Nutri-Food in each serving must contain 20 or more units of carbohydrates. Now let's draw the graph for the inequality. Would you like to try?
Okay, I'll start with the intercepts with the axes. When y is 0, 2x equals 20, so x must equal 10. Let me plot that. Now for the y-intercept. When x is 0, 4y equals 20, and y must equals 5. That's here. Now I can join the points with a line.
Well done. The line divides the points on the Cartesian plane into 2 areas. Now you just need to decide which region satisfies the inequality. Choose a point in one of the 2 regions and test it.
How about this point, where x is 1 and y is 3? If I substitute that into the inequality, I get 2 times 1 is 2, plus 4 times 3 is 12. 2 plus 12 is 14. 14 is less than 20. So this point does not satisfy the inequality. I guess the points on the other side of the line are the ones that will satisfy the inequality.
Just to be sure, let's check that by testing a point on the other side of the line. Let's take 6, 5. X is 6 and y is 5, so we get 2 times 6 is 12, plus 4 times 5 is 20. 12 plus 20 is 32. 32 is more than 20, so this point definitely satisfies the inequality. You could test some more points, but you will find that the points on this side of the line satisfy the inequality. To show this, we can shade the whole area. The shaded area shows all combinations where there are enough or more than enough carbohydrate units in the mixture. We can do the same for each constraint in the mixture that the dietitian is making. If we do them all, we end up with these graphs and these shaded areas. This shaded area shows all combinations where there are enough or more than enough protein units in the mixture, and this shaded area shows all combinations where there are enough or more than enough fat units in the mixture. Compare this with what we found when we crossed off points on a grid. Do you see that the shading of the linear inequalities lies within the feasible region? The feasible region is the area where all 3 graphs are shaded. The crossing off of points kept the feasible region clear, but we'll sort this problem out in the next lesson. For now, here's your task for this lesson. Check that you understand how to graph inequalities and draw the graphs of these linear inequalities.